This video lays out the very basics of how we are going to introduce stochastic volatility into return shocks. Now let's connect back to the basic return decomposition, where the return equals mu t minus 1 plus epsilon t, where epsilon t is a white noise process. So we start with the basic question. Where shall a time-varying conditional volatility come from? Well, looking at the decomposition, it's evident that it can only arise from epsilon t, because any time variation in mu t minus 1 is predictable as of t minus 1, and does therefore not contribute to the conditional squared deviation from the mean. Hence, if we want to incorporate stochastic volatility in returns, we need to get rid of the assumption that sigma square epsilon is a constant. Said differently, we need to abandon the assumption that volatility is homoscedastic, but rather treat it as heteroscedastic. Now let's continue with a question. Why care about time-varying volatility? Well, volatility is of first order importance to an investor. It quantifies the expected squared dispersion around the expectation. If volatility is close to zero, time variation doesn't matter much, as realized returns will anyways be very close to the expectation. But if volatility is high, you know that future realizations will likely be far off from your expectation. And volatility is one metric to quantify by how much you could be off. Now, whether a stock's annual return volatility is 15% or 80% makes a huge difference. And asset market volatility varies considerably over time. There are periods where annual stock market volatility has been below 15%, while in other periods, like the 2008 financial crisis, it was above 80%. Just visualize a Gaussian distribution with a zero mean and its two standard deviation bounds for future realized returns. With a 15% annual volatility, you shouldn't be too surprised to lose 30% in a year. But if annual volatility was 80%, you should prepare to lose everything. So for asset management tasks, like determining a Markowitz optimal portfolio, or for risk management issues, or for option pricing and the like, having a good estimate for future expected deviations from the mean is crucial. Therefore, let's generalize the return decomposition as follows. The return in RT has the predictable component mu t minus 1 and the unpredictable epsilon t. Now epsilon t will be the product of sigma t minus 1 times eta t. And eta t is a white noise process with variance 1. Now the mu t minus 1 is as previously, it's the conditional forecast of RT as of time t minus 1, and sigma square t minus 1 will be the conditional variance of RT, conditional on time t minus 1 information. Now remember, as shown in previous videos, the predictable part of a return, the mu t minus 1 component, can be modeled by an ARMA-PQ model, potentially extended by exogenous predictable variables coming from the CAPM, the Fama-French model, or using the dividend yield or any other factor risk model. Now we refer to sigma square t minus 1 as the conditional one step ahead return variance. And that variance measure is a random variable, but it's predictable. And in fact, variance is much more persistent than returns. This says that one is able to predict whether something is going to happen, but not the direction. There's one caveat that we need to address right away. An asset's return variance is not observable. And that is a problem. For example, how can we judge whether we have come up with a good model for variance if variance is unobserved? I will tackle that issue in a follow-up video.